Yeah, hello everyone. A very good evening. I hope I'm audible and visible. So, anyone of you can confirm me? So, okay, let's start the session. So, yeah, hello everyone. My name is Pooja Varma. I am PMRF Research Scholar from IIT Kharagpur, and instructor for this course is Professor Shantanu Chattopadhyay from Electrical and Electronics Engineering Department, IIT Kharagpur. This is a week 8 live interactive session on digital circuits. You can use chat box for asking and interacting, and also you can unmute yourself if you have any doubt, and you can ask. So I hope all of you have gone through this week video lectures. So the basic topics which have been covered is finite state machine design procedures, data converters, in data converter, digital to analog converters, and analog to digital converter, and in which this DACs are binary weighted resistors, R to R ladder, and analog to digital converter successive approximation, analog to digital converter, flash, analog to digital converter, and dual slope analog to digital converters. So these are the some topics which have been covered for this week video lectures. Okay, let's start from the questions. So first question for this week is the advantage of using a dual slope ADC in a digital voltmeter is that option A, its converge time is small. Option B, it gives output in VCD format. Option C, its accuracy is high. And option D, it does not require a comparator. So any one of you can answer this question. Okay, what is the advantage of using dual slope ADC in digital voltmeters. So would you like to answer this question? Okay, so option C is the correct answer. Its accuracy is high. The advantage of using a dual slope ADC in digital voltmeter is that its accuracy is high. Okay, actually dual slope ADCs are the most accurate type of analog to digital converters because they are not affected by variations in components values caused by noise. Okay, this is the reason for its accuracy is high. So correct answer for this question is C. So dual slope ADCs are used where we need a high accuracy. Okay, so this is the advantage of the dual slope ADC. Okay, so moving to the next question. So next question is the fastest ADC is, which one is the fastest analog to digital converters? Option A is a counter type, option B is flash type, option C is successive approximation, or option D is dual slope type. So which one is the fastest analog to digital converters? Yeah, flash type ADCs are the fastest. Dual slope is the highest accuracy, which has highest accuracy, but not fastest. Right? In the previous question, they have asked dual slope for highest accuracy. Okay, so this is a basic structure of a flash type ADCs. So flash type ADCs are the fastest type ADCs because they can convert analog signals to a digital signals in a single step. Okay, whatever analog signal we will give, it will convert in by this structure because there are multiple op-amps or comparators are used. So it will be the fastest, and then it will go to the encoders. So flash type ADC or flash analog to digital converters is the fastest type ADCs among all other ADCs. It is also known as a parallel analog to digital converters. Okay, it comprises high speed comparators. These are the resistive voltage divider circuits. This make a voltage divider circuits and a priority encoder. So for n with flash ADC, if we want to convert, so 2 to the power n minus 1 comparators are required to convert analog signal to digital signal. It depends how many bits we need for conversion. N is the number of bits. Okay, so flash type ADCs are the fastest. That's why option B is the correct. Now, next question is which ADC has fixed conversion time? Option A is counter type, option B is flash type, option C is dual slope type, or option D is successive approximation type. So, can you answer this question? Please answer in the chat box. Which ADC has fixed conversion time? Either it is a counter type, option B is flash type, option C is dual slope type, or option D successive approximation type. Already answer I have given here, that is option D is the correct answer. Successive approximation has a fixed conversion time. So this question is there. Successive approximation ADCs has a fixed conversion time because the conversion process is done in a fixed number of steps regardless of the input signal. So the conversion time in the successive approximation ADC depends on the number of bits used for the conversion, that is n. Okay, so the conversion time is calculated for successive approximation is n into t clock. Okay, it is the time period of the frequency. The successive approximation has a fixed conversion time among this, and all other it is varying. Okay, so now next question is find the full scale output of a 4-bit DAC produces an output of 0.1 volt for a digital input 0001. So what will be the full scale output of a 4-bit DAC? Produces an output of 0.1 volt for a digital input 0001. So how we will calculate the output voltage? That is full scale output voltage. Okay. So for digital input 0001 already the output is given, that is 0.1 volt, and they are asking what will be the full scale output for 4-bit DAC that produces an output of 0.1 volt for input 0001. So the formula is already, I think you know that if you have gone through the weak video output voltage V0 is equal to resolution into decimal equivalent. This is the equivalent of binary. Input. Okay. So what is a decimal equivalent this binary? That is 1, right? If you convert it, that is 1. Okay. So since DAC is a 4-bit, it can get a maximum value of 111, right? It is a 4-bit. So what will be the maximum value? That is 1111. So what will be the decimal equivalent of this? That is 15, right? Okay. So which decimal equivalent is 50? So for 1, for this one, it is produces of 0.1 volt, output of 0.1 volt. So for 1, it produces an output of 0.1 volt. It is given. So for 15, it will produce. So for 15, what it will produce? That is simply 0.1 into 15, because they are asking what will be the full scale. That is 1.5 volt. Okay. So it is already given for the digital input 0001. The output is 0.1. Now 4-bit DAC product. There is given also this is the 4-bit DAC. N is equal to 4. So what will be the full scale voltage for this? So in order to find out the full scale, we need to take a maximum. What will it will go? That 4-bit, that is 2 to the power 4 minus 1, right? So 16 minus 1, it will go up to 15, 0 to 15 for 4-bit. So that's why we have taken the maximum decimal equivalent and then multiplied by 0.1 into 15. So that we will get 1.5 volt. So that's why option A is the correct answer for this question. Okay, have you understand this question? Can we move to the next question? Okay, so moving to the next question. So next question is, what is the output of the following circuit? For the input is given B4 is 1, B3 is 0, B2 is 1, B1 is 0, and V reference is given as a 16 volt. Okay. So what is the output of the following circuit? So here V reference is given, and here V4 is LSB. Okay. Least significant bit. And B1 is MSB. So we can write it from 0, 1, 0, 1, right? Here it is a B4, it is B3, B2, and it is B1. Okay. So B1 is 0, B2 is 1, B3 is 0, and B4 is 1. Right? Okay. So what will be the decimal equivalent of this? That is 5. Right? Okay. So as we know that R2R ladder network output is the output voltage is, we can find out voltage is, that is V naught equal to minus V reference, it is also given in slide, B3 1 by 2 plus B2 1 by 4 plus B1 1 by 8 plus B0 1 by 16, right? But here it is given only B1, B2, not from it, B0, B1, B2, B3, B4. So we can write it like this also, minus V reference is equal to, so here LSB is B4 and here it is B0. So we will write from this direction. Okay. So B1 1 by 2 plus B2 1 by 4 plus B3 1 by 8 plus B4 1 by 16. Okay, in normal case B0 is the LSB, but here it is given B4 is the LSB, so we have to write in terms of our question. Okay, so here already given V reference is given, that is 16 volt, so I am putting it here, say minus 16, and put all values of V1, V2, V3, V4. So B1 is 0, so 0 into 1 by 2 plus B1, B2 is 1, 1 into 1 by 4, B3 is also 0 into 1 by 8, and B4 is 1, so 1 into 1 by 16. Okay, so minus 16, it will be 0 plus 1 by 4 plus 0 plus 1 by 16. If we further calculate it, it is 16. Minus 16, so 1 by 4 plus 1 by 16. So if you will get 16, 5 by 16, right? So 16 and 16 will be cancelled out. You will get, I'm writing it here. V0 is equal to minus 5 volt. Minus 5 volt, right? 16 and 16 will be cancelled out. So minus 5 will be left. So V0 output voltage is minus 5 volt. Okay. That's why here it is given. Option C is the correct answer for this question. Okay. And there is another way to solve this question also. So I can So V0 is minus 5 volt for this question, or we can solve by this question, this type of V out is equal to, or V naught is equal to minus plus minus, you can say V reference divided by 2 to the power n into V in, or decimal equivalent of this binary. This is a decimal equivalent of this binary. So V reference is given, that is 16 volt. We can take minus here or plus. So it is a 4 bit, right? So 2 to the power 4. And what will be the decimal equivalent is? That is 5. So that is 16 by 16 into 5. You will get only 5 volt. Here it is a plus minus. So minus, it is given in all minus. So you can take minus 5 volt. You can solve either this way or this way. Both way. So answer is a minus 5 volt. Okay. Okay, so I hope all of you understand this question. Moving to the next question. So next question is, output of the Mealy machine depends on. So option A is present input only, option B the present state only, option C both A and B, and option D is none of the above. So this is a very basic question. I think you can answer also I have written them. So can please any one of you can answer this question? Just test it. Can able to answer this question? Don't want to give answers. Okay. So output of a Mealy machine depends on the present input as well as the present state, both. While in the Moore machine, it depends on the present input. So in a Mealy machine, output is depend upon present state as well as present input. So option C is the correct answer. Okay, it depends on both present input only, and yeah, correct, Neetu. Thanks for trying. So the present state as well as present input. The Mealy machine output depends on both. Okay. Okay. So moving to the next question. So next question is also related to Mealy and Moore machine. So compared to a Moore FSM finite state machine, a Mealy FSM might option A have fewer state, option B have output generally one clock cycle earlier, option C have more states, or option D both A and B. That means have fewer states as well as have output generally one clock cycle earlier. So compared to Moore FSM, a Mealy FSM might be. So option here, option D is correct. Both Mealy machine have fewer states than Moore FSM, and output generally one clock cycle earlier to a Moore FSM. Okay, so a Mealy machine has fewer states as compared to a Moore machine based on its present state and the current input. The Mealy machine alters its output. It places its output on a transition. Every Mealy machine reacts to the input comparatively faster than Moore machine because they react in the same cycle. They don't wait for the next clock. Okay, so that's why the Mealy machine is faster, have fewer states as well as faster than Moore machine. Okay, so option D is the correct answer for this question. Okay, so moving to the next question, I think you can also try this question. This is a basic. Already told what will be the formula for the getting the number of comparators in a 4-bit flash ADC is. So question is the number of comparators in a 4-bit flash ADC is option A is 4, option B is 5, option C is 15, or option D is 16. So formula is to getting the number of comparators required in a 4-bit flash ADC is, so number of comparators required in 4-bit flash ADC is, the formula is 2 to the power n minus 1, where n is a number of bits. So here it is given 4 bit. So 2 to the power 4 minus 1, that is 16 minus 1, that is 15. So 15 comparators are required for 4-bit flash ADC. That is correct option is C. C is the correct option, that is 15. Okay. So okay. I hope you understand this question. So moving to the next question. So next question is the state diagram of a finite state machine designed to detect an overlapping sequence of 3 bits is shown in the figure. The FSM has an input in and an output out. The initial state of a FSM is a S0, that is this one. If the input sequence is, that is 1010110100001101, starting with the leftmost bit, that means this side, then the number of times out will be 1. How many times the out will be 1 while moving in this input sequence? So let's check it. For how many times the out will be 1. Okay, so first is 1, right? So let's see, when in is equal to 1, then the when the states are where the states are moving. So here it is 1, so it moves from in is 1, right? And just I will write it here, 1 0 1 0 1 1 0, then 1 double 0 1 1 0 1. Okay, so I'm starting from here. So when in is equal to 1, then out is equal to 0 here. It is moving from state 0 0 to 0 1. Now next input is 0. Okay, so it is already in state 0 1. So let's check, in is equal to 0, then when where it is moving? It is moving 0 1 to 1 0. Here out is 0. Okay, so here out is 0. Now again next is 1, and now it is in state 1 0, right? Then what in is 1, this is 1. Okay, now it is moving 1 0 to 1 1. So but here out is 1, so I am writing out is equal to 1, here in corresponding out. Okay, so here it is. So next bit is 0. Okay, so it is when in is 0, when it where it is going, it is going to again 1 0, right? This one, in is 0, out is 0. And where in is, when it in is, then it will move to 0 1, but here in is 0, so out is 0. It is again move back to 1 0. Now next one, next in is 1 and out is 1. Okay, again it move 1 1, again it is 1. Now next in is 1, so it will move to 0 1, right? But here out is 0. Okay, we have reached till here. Now we have moved on state 0 1. Okay, now next in is 0, it is 0, and out corresponding out is 0. Now it moves state 1 0. Again in next input is 1, so in is 1, out is 1, right? It moves to state 1 1. Now in is 0, so out is 0, again move to 1 0. Okay, so but here the next input is 0, so from this state it is moving to 0 0. but here it is 0. Okay, it again the initial state that is 0 0. Now next in is 1, out is 0. Again in is, now next in is 1. So in here, we are here, in is 1, out is here. It will again in the same state, that is out is 0. Now next it will be same, in it 0, out is 0. Now again next input is, it is in this state, in is 1, out is 1, right? So for, so the number of times out will be 1 is, so let's count 1 1 2 3, 1 2 3 4. So 4 times out will be 1. So answer is 4. Okay, just we need to track this input, where it, at which state it is going on, and note down the corresponding out. Okay, so in that case you will able to find out the number of times out will be 1. Okay, so therefore times out is 1, so total number of times out will be 1 is 4. Okay, so answer is 4, this for this question. Okay, so I hope you understand this question. So can we move to the next question? Okay, can you repeat? Okay, I am repeating it once again. So in the question, it is given the state diagram is given. Okay, so it is designed to detect overlapping sequence for 3 bits, is shown in the figure. So FSM has input that is in and output that is out. Okay, so initial stage is 0, that is 0 0. Okay, so input sequence is given, this is the input sequence for this, and it is given starting with the leftmost bit, that means this one. Okay, then the number of times out will be 1. At how many times the out, that out is will be 1 during this sequence. Okay, so now we need to find out the number of times the out will be 1 at this sequence. Okay, so
Ma'am, that
start.
is mostly is it?
Yeah, what you are saying,
That is MS.
that is,
Ma'am, that is MSB.
yeah, this is MSB, but it is given starting with the leftmost bit. So we need to take here from this side.
Okay, okay, okay,
Leftmost bit means this one is a rightmost bit. Okay,
okay, okay.
this one is MSB, this one is MSP, most significant bit. This is a LSB, but here it is given leftmost bit. So we will take from
Okay.
the leftmost. Okay, so now we are moving from the initial state, that is 0 0, right? First we are in 0 0, but here in the input sequence it is given 1. So we will see at in, when in is equal to 1, at which state it is moving. It is moving from 0 0 to 0 1, but corresponding out is equal to 0, right? So that's why I have noted here, because tracking these outputs so that we are able to count it, how many times the out will be 1. Okay, so just go through the input sequence and find out how many times and move with the sequence. So when in is equal to 1, out is equal to 0, just note it down that. Now next sequences, we have reached 0 at state 0 1. Now the in is 0, so it is from our in is 0, it is moving to the next state, that is 1 0, but corresponding out is 0. So that's why I have noted down here 0. Now next for the check for next bit, that is 1. For 1, when in is 1, out is 1, that's why I have noted down here. It is moving 1 0 to 1 1. Okay, in this state. Now we have reached till here. Now next bit is 0. So for 0, for in is equal to 0, it is going to 1 0, state 1 0, but corresponding out is 0. So note it down here. Now check for the next bit, that is 1. So for 1, where it is going? It is going to state 0 0, right? And where we are? Here, I think it is here. 1 0. Now for in is equal to 1, here it is written for here, yeah. So for in is equal to 1, it is for in is equal to 1 at this stage. Just a minute. For in is equal to 1, it is out is equal to 1. Okay, so here we have, so now again we have moved state 1 1, again input is 1. Now next input is 1, so for next input in is 1, so it is moving to state 0 1. Okay, and corresponding out is 0. So it has moved now at state 0 1. So now check for next input is 0. So and input is 0 for this, it is moving 0 1 to 1 0. Out corresponding out is 0. So note down again, next in is 1, corresponding out is 1 here. Okay, it is moving 1 0 to 1 1. Now next again input is 0, check it here, and corresponding out is 0. Okay, it is moving again 1 0. Now next is in is 0, and corresponding here in is 0, check for here, and out is 0. So it has moved to the initial state 0 0. Okay, now again next in is 1, this one in is 1, corresponding out noted down, that is 0. It move again 0 1. Now next in is 1, that means in is 1, so it will remains in the same state, that is corresponding out is 0. So noted down again, in is 0, so that means it is moving again 0 1 to 1 0, corresponding output noted down. Now next last one is 1. Okay, so we are here, so in is 1 and corresponding out is 1, so noted down. Okay, so now check for how many times it is 1, out is, that is 4, right? 1 2 3 4. So that it is asked in the question, then the number of times out will be 1 is, okay, that is 4 times the out is 1 for this sequence. Okay, I think now you have understand this question. Okay, okay, so moving to the next question. So next question is, let x is the input sequence whereas z is the output sequence. Okay, for the state machine shown below. For this one, which of the following options correctly describe the output z sequence for the input sequence x is given below? For this input sequence, what will be the output sequence? So in a same way, we again find out the answer for this question. So can you try this question in the same way? Just take inputs, that is 0 0 in this form, and move with the input states, okay, where it is going on. Again, for clarity, you can write the input and track the corresponding output. So here in X is the input sequence and Z is the output sequence. So we need to find out the that sequence. Here they have asked how many times the that output sequence will be 1. So just we need to write it in this way in the next question. So here input sequence is given, that is 0 0 1 1 0 1 1 0 1 0 1 1 0 1 0. Okay, so I have left with the shortest, so I have written like this. I can write it again, just a minute. So input sequence is 0 0 1 1 0 1 1 0 1 0 1 1 0 1 0. Okay. Okay, yeah, right. We need to track corresponding output for this input. So let's start. S0 is the initial state. So we will start from here. For tracking this output or input sequence or find out, we have to start from the left, this leftmost. Okay. So let's start from that 0. So for first, we are starting from S0. So when input is 0, the corresponding out is 0. Okay. So for here I am writing here 0. So it is moving from state S0 to S2 for input 0. And when input is 1, so it is moving to the S1. Okay. So just we need to track it. Okay. It is moving to the this way. So now we have reached to state S2. Now next input is 0 again. So for next input is 0. So let's see. So where it is going? It is again coming in the same state. Okay. And what is the corresponding out? That is 0. So here it is input, it is an output. It is written in this way. Input, this one is a output. Okay. So now again we are in the same state, that is S2. What in the next input is coming, that is 1. So where it is moving for 1? It is moving to the S4 and corresponding out is equal to 0. Okay. For this S2 to S4 and corresponding out is 0. Now we have reached S4. Now next input is coming, that is again 1. Okay. 1. Then what will be the correspond where it is going and corresponding out? So anyone of you want answer this question? For this input 1, we are currently at stage 4. State 4. What will be the corresponding out? Is
S3 1.
yeah, S3 1. Correct. Right. Now we have reached S3. Now next input is 0. So what will be the out and where it is going on? Here it is going on for 0. Out is 0 and it is moving to S5. Okay. Now next input is 1. Okay. So for 1 it is moving again S4 and corresponding out is equal to 1. So we have reached S4. Now next input is 1. So again it is going to S3 and corresponding out is equal to 1. Okay. This is 1. Now next input is 0. So for 0 again it is going to S5 and corresponding out is equal to 0. Now next input is again 1. So for 1 it is again moving to S4. Now next is 0. We have reached here. Now next input is 0. So it is going to S2 and corresponding out is 0. Okay. Now we have reached here. Now next input is 1. Okay. So for input 1, it is again going to S4, corresponding out is 0. Now again it is 1 and moving to the state S3 and corresponding out is 1. Okay, now again it is 0. So it is again going to S5 and corresponding out is 0. Now next is again 1. It is again going to S4, corresponding out is 0 again. It is 0, so it is moving to S2 and corresponding out is 0. Okay. So now the output sequence that we have got, that is Z, is 0 0 0 1 0 1 1 0 1 double 0 1 0 1 0. Okay. Now we need to match it to the answers. Then we are able to find out which option is correct. So just 0 0 1 0 double 1 0 and 0. So option A is the correct answer. It is matching with the option A. So option A is the correct answer for this question. Okay, so yeah, I hope all of you understand this question. So can we move to the next question? So, okay, I hope all of you have got this question. So moving to the next question. So next question is given: an 8-bit DAC digital to analog converter has a reference. V reference is -5 volt. What is the output voltage when B in? This is given the binary input. Assume Rf is equal to R by 2. Okay. So already we have seen this type of problem. So for digital to analog converter, the output voltage is V out. The formula is V out is equal to plus minus V reference 2 to the power n into V in, where it is a decimal equivalent of binary sequence. Decimal equivalent to binary. Okay, first we need to find out what will be the decimal equivalent this binary. So B in is given, that is 10110100. So can anyone of you convert it? How much it will be? What will be the decimal equivalent of this binary sequence? So already we know that how we can convert it, that is 2 to the power 0, 1, 2, 3, 4, 5, 6, 7. Okay, so that is 128 plus 32 plus 16 plus 4, right? If you add this, then you will get 180. That is the decimal equivalent of this binary sequence is 180. Okay, yeah, right, me too, 180. So now we can put it here. So V out, V reference is given, that is -5 volt. So we can take here plus minus. Here the answer is given in a positive form, so we can take here negative and then we will, and 2 to the power n into 180. So n is given here 8 bit, it is 8 bit, right? So 5 divided by 2 to the power 8 into 180. So what we will get? 5, 2 to the power 8 is 256, right? Into 180. Now if you multiply this, so you will get 900 by 256. So if you divide it, you will get 3.51. You can check it. Okay, 3.51 volt. Okay, so that's why option here is the correct answer for this question. So anyone of you can check it. What will, after dividing, what you will get? 900 divided by 256, what you will get? Can you answer in the chat box? Can you divide and check it? What will be the answer? And also I will suggest you, please check with the another uh, type. I have given you the other way also to solving this problem, this type of problem. Okay, so you can divide it and check it whether it is coming 900 divided by 256 is equal to 3.51 or not. Okay, so you can check it. Okay, so moving to the next question. So next question is, in DAC, digital to analog converter, it is a dash, is defined as the variation in analog step size between successive bits. That is option A, differential nonlinear error, option B integral nonlinear error, or option C resolution error, or option D full scale error. So in DAC is defined as the variation in analog step size between the successive bit. It is a differential nonlinear error, either integral nonlinear error or resolution error or full scale error. So it is a differential nonlinear error. Okay. So in the differential nonlinear error, analog step size changes with increasing digital input. Already you have seen in that video lectures that the step size changes, then the differential error or linear error. Measure the largest deviation between successive bits. Okay, so it is a differential nonlinear error. While the integral nonlinear error is defined amount of deviation from the straight line after offset and gain error removed on a concurrent bit. Okay, so it is in a DAC, differential nonlinear error is defined as the variation in the analog step size between the successive bits. It is defined by differential nonlinear error. Okay. So moving to the next question. So next question is, the figure below shows the 3-bit flash ADC circuit. What would be the encoded binary output, that is D0, D1, D2, when V is given as 8 volt here and V in is equal to 3.45 volt. Okay. This is a 3-bit flash type ADC. So how we can solve it? Okay, so I'm solving it here. V is given as 8 volt and V in is given as 3.45 volt. Here that 8 volt is given to the voltage divider circuit here to the op-amp. So what is the function of op-amp? It will compare the two inputs, right? At this positive and negative, what will be the greater? That is V in is greater than that V reference. You can say V reference. It will generate a 1, or you can say this will be generate a positive output, that is 1. If it is less than that, V in must be greater than that V, so it will generate 1, otherwise it will be the 0. Okay, so let's check what will be the corresponding inputs of that corresponding points in order to compare. Here V in directly given to the positive input of the op-amp, right? This one is a positive one. Are you able to see that? I cannot. So this one is a positive, this one is negative. Negative inputs are connected to the voltage divider circuit. So we need to find it out. What will be the exact input we are giving? So we will get it from the, here already it is given 7V by 8. So we need to put the value of that V. So for first op-amp, so I'm writing here what will be the V reference or the V input for the first op-amp of the negative. In the positive input, it already we are giving 3.45. Okay. So here it is a 7V by 8. So V is given as a 8 volt. So 7 into 8 divided by 8. So here we are getting the 7 volt. Okay. In the first op-amp. So 7 volt, but our V in is 3.45 volt. So here V reference, that means negative input voltage is greater than V in. So that will generate the output 0. Okay. Now check for the next op-amp, that is second. Here the input is 3V by 4. Okay. Here it is a 3V by 4. Okay. You can find it out by voltage divider circuit also. What will be the output if you have studied this? So 3 into 8 divided by 4. So you will get 6, right? 6 volt at this point, and here in the positive input it is a 3.45. Again, it is greater than the Vin, that is 3.45. So it is greater than in the negative input, so it will generate the output again 0. Okay, so it will generate 0. It is also 0. Now check for the next op amp. Third one, the input is this one 5V by 8. So 5V by 8, again 5 into 8 divided by 8, you will get 5 volt. Here again it is greater than Vin because Vin 3.4, right? So again it will generate 0 output. So 0. Okay. For fourth op amp, now check that one is V by 2. That is 8 by 2. We will get 4 volt. Again it is greater than Vin. So again it will generate output 0. Okay. Now check for fifth one. That is 3V by 8. 3V by 8. Yeah. So 3 into 8 divided by 8, that is 3 volt. So here 3 volt is less than V because it is 3.45. So the positive input is greater than the negative. So it will generate input 1. Okay. Now check for sixth one. The sixth one is V by 4. So we will get V is 8 by 4, that is 2 volt. It is also less than VE, so it will generate output 1. Now last one, seventh op amp, it is V by 8. So 8 by 8, that is 1 volt, which is less than VE. Okay, yeah. So again it will generate output 1, right? So the output of the op amps are 0, 0, 0, 0, 1, 1. Okay, this is the input of that priority encoder, right? So these are the inputs of the priority encoder. So for how many inputs are 1? The last 3 are 1s, right? So, so 3. So what will be the decimal equivalent? The 3 inputs are high. 0, 0, 0, 1, 1. Okay, so here we will check the 3 inputs are high. So what will be the corresponding binary equivalent for that 3 input? That is 0, 1, 1. That out priority encoder will produce if it is maybe let's this one will be high or this one. So what will be the or it is also high. So what will be the corresponding output? So have you understand how it is coming?
Ma'am, last step is not clear. Last step.
Okay. So here
Output of priority encoder.
okay, so here 3 inputs are high of the op amp, right? 3. Just
Yeah.
check for the 3. What will be the binary equivalent for 3? How we can write? That is 0, 1, 1. Because here 8
Three
into 3.
number of bits. Okay,
Huh,
number of bits. 3 bits are high. So
huh,
for 3 we'll write the binary equivalent zero
yeah,
one one.
0, 1, 1.
Oh,
Okay.
okay. That will be
So
D, not D1, D2.
yeah, yeah. And if that one will be high, then what will be the binary equivalent for this one? 4. That will be the 1,
10000.
yeah. So for 4, if the 4 inputs are high, then we can write it like this. But here the 3 inputs are high, so we can write it 0, 1, 1. Okay. So now I hope all of
Okay.
understand this question. Okay.
Okay. Thank you.
Yeah.
Ma'am, can you repeat that last step?
Okay, so what I have told you, the three inputs are op-amp are high, right? So 3 in the decimal, how you can write in the binary for the 3? That is 0, 1, 1, right? What will be the 3? That is 8, 4, 2, 1. So it is a representation of 3 in a binary. Yeah, are you listening? So here,
7.
yeah, the 3 inputs are high. So it is a priority encoder. It will give the priority to the those inputs which are high. So it will give only that 3. Okay, so we need to check what will be the three inputs are high. Just focus on the three inputs are high. So if three inputs are high, what will be the binary equivalent? That is 0, 1, 1. So for example, if I am saying that the four inputs are high, that is. So what will be the binary equivalent of the four inputs are high? If four inputs are high, what will be the binary equivalent? That is 1, 0, 0. Because here we can produce only three outputs. Okay, 8 instead 3 binary encoder it is there. So we have to take it output like this. If it is four inputs are high, so we will take a binary equivalent of 4. Okay. So that is represented by 1, 0, 0. But here three inputs are high, so we can represent that binary, that is 0, 1, 1. Have you understand this now? Just focus on 3,
Yes, yes.
4.
Okay, okay.
Okay. Okay. So option A is the correct answer for this question. Okay. So moving to the next question. So next question, in a 5-bit successive approximation ADC with reference voltage of 1 volt. Okay, here reference voltage is given 1 volt. If the input voltage is 0.67 volt is applied after 3 clock pulse, 3 clock cycle, the content of the successive approximation resistor is. What will be the content in the after 3 clock pulse? Okay, so it is given, it is a 5-bit successive approximation ADC. Reference voltage is given, input voltage is given, and we need to check after 3 clock pulse what will be the content of the SAR. Okay, so just here we need to take assumptions and then we will check it out. So assume that initially all bits are 0, right? Initially, so initially all bits are 0 in successive approximation register. Let's, that is, it is a 5-bit, so we have to reprint the 5 bits. Okay, initially all bits are 0. So when, just I'm writing, when clock pulse 1 is coming, pulse is a pulse, clock pulse 1 it is coming. So let's we assume that V5 is 1. Here we need to take assumptions, and now we need to, let's assume that the last one, that is V5 is 1. So here we will take, then we will prove it. Okay, so let's assume that V5 1, then bits are in the successive approximation register will be this one. Right now we will check whether it is 1 or 0. So if let, we can take it like let. So what will be the V1? If you have gone through the SAR, you will get the what will be the 1 by 2 by V reference. Okay, so V reference is given 1 volt, so it is 1 by 2, that is 0.5 volt. Okay, but V in is given, that is 0.67. So here V in is greater than V1. Okay, here we need to compare here. Then we will check. So V1 is less than Vin. So here Vin is greater. So that means that will produce output 1, right? In the previous we have also seen that in this one when it is greater than, then it will produce output 1. But it is successive approximation type register. In the previous somewhere we have studied that where we have studied. So you can remember all these formulas where we have used like this. So we have to take this one B5 1 by is we are using this formula. Okay, just I can write it here also. So here we are using that V out will be V reference, that is the MSB, then 1 by 2, that is V3. Here I am writing for 4 bit, plus 1 by 4, that is V2, 1 by 8 for V1, plus 1 by 60 for B0. So you can write it for 5 bit also, that is 1 by 2 for B4, 1 by 4 for B3, 1 by 8 for B2, 1 by 16 for B1, and plus 1 by 32 for B0. Okay. So here Vin is greater than V1. What we have it? So that means that bit must be, that will be 1. So that means the now final after first clock pulse, the content of the SAR is, that is 1 0 0 0 0. Okay. Now check for the next clock pulse. For the next clock pulse, let clock pulse 2. Let, here we have already checked that for V5 V5 is 1. Now we check for V4 whether it is 1 or 0. Okay, now assume that V5 and V4 both are 1. Already we know that now V5 is fixed, that is 1, because V1 is less than V in. If it is greater than V1 is greater than, it will produce the output 0. That means that statement is false. Whatever assumption we have taken, that is false. Okay. So now for next clock pulse, the output at that point, just check for that is 1 by 2, last one, plus now next one, that is B4. It is multiplied by 1, so I am not writing here because that is 1. So 1 by 4. Okay. So what will be the answer into V reference? Okay. So we will get here 3 by 4 into V reference. V reference is 1. So we will get, what we will get? That is 0.75. Now it is V2. So V2 is 0.75, but V in 0.67. So here V2 is greater than V in. So that means that will produce 0. That means that V4 should not be 1. It must be 0. In that case, the what will be the content of the second clock pulse? That is 1 0 0 0 0. That assumption is false because V2 is greater than V in. That input voltage must be greater than that one, then will take. Now check, similarly check for the last clock pulse, that is they have asked after 3 clock pulse what will be the content. So check for the next clock pulse. So clock pulse 3. Now already we know that V5 is equal to 1, V4 is equal to 0. Now check, let's take assumption for V3. Let's V3 is 1. That third bit is 1. So now find out what will be the voltage of that corresponding input. So V reference, that is V5 is 1, that means 1 by 2. For next bit it is 0, so it will automatically it will be 0. So for V3 it will be 8, right? V reference into how much? 5 by 8, right? 5 by 8. V reference is 1, so 5 by 8 only it is 5 by 8. What will be the, what we will get after dividing? Anyone of answer this one? That is 0.625. Okay. So where I can V3, I'm writing it here. V3 you will get 0.625. Okay. Here V3 is less than V in, right? That means that will produce output 1, that is 0.67, but here we have got 0.62. So V in is greater than V3. So that means that V3 bit is 1. Okay. So what will be the content after 3 clock pulse? The content will be 1 0 1 0 0. Okay. They have asked for only what will be the content after 3 clock pulse. So we have checked for the 3 clock pulse only. You can go to up to 5, but in the questions they have asked for only 3 clock pulse. So we have to check and find out what will be the content of the 3 clock pulse. So after 3 clock pulse, the content is 10100. So which one is correct? That is option A is the correct answer for this question. So are you getting this question? How to solve it? Just we have to take the assumption initially. Assume that all widths are 0. Then take an assumption. Let's last one MSB is the 1. Then find out by this question what will be the inputs. So all the V3, V2, V1, V0 are 0. So 1 by 2 into V reference only. So you will get the V1, then compare it with the input voltage. If it is input voltage is greater than that reference voltage, then it produces output 1. That means assumptions what we have taken left, that is true. If it is less than, then it will produce 0. That means that assumptions is the wrong. Okay, then we will move forward like this. Then we will check what will be the content for that SAR. Okay, have you understand this question? So I hope all of you are getting this question. So moving to the next question. So option A is the correct one. Okay. Okay. So moving to the next question. So next question is, in a 5-bit successive approximation ADC with reference voltage is 1 volt, if an input voltage is 0.3 volt is applied after 4 clock pulse of the content of a SAR is, so it is the same question as previous one. It is also 5-bit successive approximation, but here input reference voltage is same, but input voltage is given 0.3 volt. So in a same manner you can check it and you can find out what will be the answer for this question. So would you like to check it or would you like to try this question? You can try it and answer in the chat box in a same manner. Okay, so initially assume that all the contents in SR initially all the contents are 0 0 0 0 0. It is a 5-bit SAR, successive approximation register. In a same manner, check for the clock pulse 1. So I am just numbering it. Just take it as a clock pulse 1. Okay, here they have asked for 4 clock pulse. What will be the content of after 4 clock pulse? Okay. So yeah. So yeah, assume that for I am writing it at 1, that is 1 clock pulse. Okay. So for clock pulse 1, let, usually as we have done, let V5 is equal to 1. Sorry guys, I have lost my connection, so I'm continuing from there. So initially assume that let V5 is equal to 1 and check in the same manner for V1. Just check for what will be the output, that is 1 by 2 V reference. So V reference is 1, that is 1 by 2, that is 0.5. So let's check whether V1 is greater than V in, because V in is 0.3 only. So that will produce 0. That means that we have taken whatever assumption that is wrong. That means V5 is equal to 0. So content of the SAR is after 1 clock pulse is 0, 0, 0, 0, 0. Okay. Same. Now check for the next clock pulse. Let V5 is equal to 0. Already we have done that. But V4 is equal to 1. Now check for the voltages, that is, now next one is 1 by 4 into V difference. That part you can check by that formula. Already I have written in the previous slide. Okay, this one. Okay, so 1 by 4 V difference is 1. So that is 0.25 you will get, right? So now here 0.25 V2, so it is less than V in, because V in is 0.3 volt. That means whatever we have assumption taken, V4 is 1, that is true. Okay, that means V4 is true. So content of the SAR will be 0, 1, 0, 0, 0 after second clock pulse. Now check for the third clock pulse. Let V5 is equal to 0. Already we know that. V4 is equal to 1. Now V3 is equal to 1. Let's assume that. Okay. So now check for the voltages. So what we will get? That is 1 by 4 plus 1 by 8 into V reference. Right? So V reference here it is 1. So what we will get? That is 3 by 8. Right? We will get 0.375. So 0.375 is greater than, so V in, so V4 is greater than V in. That means whatever assumption we have taken, that is wrong. V3 is 0. So content of the SAR will be 0, 1, 0, 0, 0. Okay, it will remain same after 3 clock pulse. Now check for the next clock pulse. For the next clock pulse, we can check it. So for the next clock pulse, just I'm getting disconnected again and again. Let me check. So okay, so content for the next clock pulse will be okay. Just a minute, I am disconnected again and again. So, okay, content of the next clock pulse after fourth one, what will be? So now let V5 already we know that that is 0, V4 is equal to 0, V3 is also equal to 0. Now check for V2 is equal to whether it is 1 or 0. Okay, so let's check for V4, that is 1 by 4 plus 1 by 16 into V reference we will get. So what we will get, V reference is 1, V reference is already we know that that is 1, that then we will get 5 by 16. What will be the output? If you divide 0.3125, if you divide it. Now again V4 is greater than V in, that V in is 0.3 volt only. That means the assumption that we have taken V2 is equal to 1, that is wrong. V2 is equal to 0. So content of the 4 clock pulse will be the content will be 0, 1, 0, 0, 0. It will be the 0, 1, 0, 0 because that assumption also false. Okay. So in that case, here also the option A is the correct answer for this question. Okay. Okay, so you have to solve in the same way, manner. Okay, for getting V1, V2, V3, that is you can get from this formula. Okay, already we have described in the previous slides also. Okay, okay. So now again moving to the next question. So next question is the sequence detector, the sequence detected by the state diagram shown below. What are the sequence detected by the diagram? So these are the options. So let's check it what is the sequence that has been detected. So already we know that we have to start from the initial state, that is state A, then where when the sequence is detected. So see only those inputs by which we can move forward direction. Okay, so just we need to note down the inputs here because we need to check whether which sequence we have detected. So for that, this one is moving in the forward direction. That means input is 1, A2, B when we are moving, input is 1 and output is 0, right? Input or output. Now for the next sequence where we are moving, next one B to C, right? So for V to C, input is 1 again, output is 0. When input is 1, then going to C. Otherwise, when input is 0, it is again move to the previous state. Okay. Now when we are in the state C, when we are moving, where input is 0 and output is 0. Okay. Now for the next state, D to A. D to A. Input is 1, output is 1. There is a 1 option and there is another option is also there. When input is 0 and output is 0, then that also it is going to the forward direction. So what are the sequence we have detected? It is in option. Okay. So 1 1 0 1 or 1 1 0 0. So in the questions already it is given that 1110 sequence detector without overlap or 1110 sequence. So that sequence we didn't find 1110. We have got that 1101 or 1101. So that has been discarded because that is not in the option. So now we have to check 1101 sequence detector without overlap or 1101 sequence detector with overlap. So we have not seen any overlap between this sequence when we are moving. Okay. That means when the input again it is going to same state or overlapping. So it is a 1101 sequence detector without overlap. So that's why option 3 is the correct answer for this question. Okay. Okay. So
Without overlap is, ma'am?
without means there is a no overlap is there. We are moving only forward direction. Okay. When we are seeing that where we are going to the when where the inputs are taking the forward direction. That means A to B, B to C, C to D, D to A. We are not going in the same state only. That means when the input are that 1 0 or 0 1 in the same state we are not moving. Understand? Sometimes we have seen in
Okay,
the previous
okay.
one we are moving in the same uh, same state, but here we are not moving in the same state. We are just going in the forward direction and reaching the previous state. And final one to A again, A to A without any overlap. Okay. Okay. So I hope all of you understand. So moving to the next question. So next question is the following state diagram represents which of the input equation. This diagram represent which of the input equations given dA is equal to ax comma y, where dA denotes the D flip-flop with output A, output is A. Okay. The x and y are the inputs to the circuit. Okay. So here it is given two state, that is 0 and 1, and input sequence is also given. X and y are the inputs, so 0 0 0 1 1 0 1 1. So in two state it is there. So A is the DA is the D flip-flop with output A. Output A is the output of the D flip-flop. Okay. So we can solve it like this. Okay. Present state, that is A. Okay. Inputs that are X and Y. Next state, that is A plus, or you can say that A dash also. Okay. So now we can make one table. So from there we can take, here the two states are given 0 and 1. We have to take that two state as a output of the D flip flop. Okay. So 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Now we have to find out what is the next state based on that. So now we have to check A is in the A has two states, that is 0 and 1. 0 and 1 with the same inputs, that is 0 0 0 1 1 0 1 1. And again for 1 it has a 4 input 0, 0, 0, 1, 1, 0, 1, 1. Okay. So now if we are in the state 0, when what will be the next stage when the inputs are 0, 0? It is in the same state, right? When inputs are 0, we are in state 0, that is, it is again moving. What is the next state of that? That is state 0, same state. Now, when the inputs are, we are in state 0, inputs are 0, 1, 1, 0, 1, 1, that is 0, 1, 1, 0, 1. Where we are moving? We are going to the next state, okay, that is 1. So, we are going to the next state, that is 1, 1, 1. That is the next stage. That is the output. You can, now we are in the state 1, right? Now, when the inputs are 0, 0, we are again moving in the same state, that is 1. And for 0, 1, 1, 1 is the same, it is 0, 0. We are moving in the same state, that is 1. For 0, 1, again, we are in the same state. The next state for the 0, 1 is 1. And for 1, 0, what is the next? What will be the state? That is 0, right? Because we are again moving to the next state. For 1, 0, it's 0, and for 1, 1 it is same, it is in the same state. Okay, so have you understand? The following state diagrams represent the input equation. What will be the input equation? We need to find out. So for that we have to make a table. Okay, here it is given D flip flop is given, and D flip flop output is A, and inputs are X and Y, that is 0, 0, 0, 1, 1, 0. We have to, but here A has taken one state is 0, another state is 1. So for both state we have to given the input 0, 0, 0, 1, 1, 0. Now we have to check when it is in state 0 for the corresponding input where it is moving. What is the next state for that? So we have written in that table format from here. Now we have to find out the state diagram that represents the input equation. So from again from the K map we need to find out what will be the equation, that is A and X, Y, because these are the inputs. It is 0, 0, 0, 1, 1, 1, 1, 0. It is 0, 1. Okay, so 0, 0, 0 is 0. So here 1, 1, 1, right? Now next one is 1, 1. This one is 0, again it is 1. So here 1 chord, 1 pair, and this one pair. So output equation state diagram represented by, for this one pair is, that is A, right? Take a common from this one, that is X dash, plus write down equation for this pair. So it is A dash, and common between these two columns, that is X. Now write down for this chord, that is, what will be the, that is Y, right? So X dash plus A dash X, what we can write it? We can write it as A XOR X, right? Plus Y. So the equation we have got, that is A X XOR X plus Y, output for the flip flop D flip flop output for DA. Okay, so this is the equation. So A XOR X plus Y. So option 3 is the correct answer. Okay, have you got this?
Yes, ma'am.
Okay. Okay, so moving to the next question. So next question is a state transition diagram with states A, B and C. There are three states A, B and C, and transition probability. These are given transition probability. What will be the transition probability to moving B to A to B, or in the same state? These are the different transition probabilities are given. Shown in the figure. Example, P1 denotes the probability of transition from state A to B. Okay, from this state diagram, select the statements which are universally true. What are the statements which are universally true? Okay, so a state transition diagram with states states are A, B, and C, and the transition probabilities are, that is P1, P2, P3. It is corresponding. Okay. So from these states, what we can find out? So that can be uh, so from a state A, the outgoing transition probability that can be equal to 1. Okay. So check for every state. So what are the overall income outgoing for a state A, outgoing transition probabilities are equal to 1. That can be followed to all the states. So let's check what are the transition, what will be the outgoing probability, that is P1, then other outgoing, that is P1, then plus P4 plus P7 is equal to 1. For the next state also, for the state B, the outgoing transition probabilities are equal to 1. What are the, that is outgoing is P2 plus P3 is equal to 1. For state C, outgoing transition probability are P5 plus P6 can be equal to 1. Already we know that the concept of the transition probability. Now we have to check the by options. So first option is P2 plus P3. P2 plus P3 is equal to 1. That already we know that. Now P5 plus P6. That means outgoing transition probability of B is equal to outgoing transition probability of C is equal. So already we know that both are equal to 1. That can be true. Okay, that option can be true because both are equal. P2 plus P3 is equal to 1. P5 plus P6 is equal to 1. Okay. Now next one is P1 plus P3, that is incoming and outgoing. A to B, B to A is equal to P4 plus P6. That can be equal to 1. No, that is not equal to 1 because we are going taking only, it is going to the different state, not in the same state. Either it is incoming or outgoing. So that cannot be correct. That is not equal to, that can have a different probabilities because they are moving in the different states. Okay, so now check for the next one, that is P1 plus P4 plus P7 is equal to 1. P1 plus P4 plus P7 is equal to 1. So P1 plus P4 plus P7. Already we have written that in the state A outgoing transition probability are equal to 1. That is also correct. Now check for the next one, that is P2 plus P5 plus P7. P2 plus P5 plus P7. These are the different states and their incoming probability at the different stage. So that cannot be correct. So only option 1 and 3 are the correct option for this question. Okay. Option 1 and option 3 are the correct one because we can't sure about that and this one. Okay. Okay, so I hope all of you understand this question. So moving to the next one. So next question is, what is the SNR, signal to noise ratio, of an ideal 10-bit ADC? So in order to find out the signal to noise ratio in dB, the formula is 6.0 n plus 1.76 dB. Okay, this one is a formula where n is the number of bits. Okay, so already it is in dB, so just put the value of n, that is 10. It is given, this is a 10 bit plus 1.76, so you will get it 6 so you will get 60.2 plus 1.76, so you will get 61.96 dB, right? So this one is a standard formula for getting a signal to noise ratio in dB. Okay, so option 3 is the correct answer for this question. Okay, okay, so moving to the next one. So next question is, a 10-bit ADC has a full scale of 10.230 volt. When the digital output is, this one is the digital output, the quantization error of the ADC in millivolt is, what will be the quantization error in the digital output? So in order to find out the quantization error, the formula is an error is equal to resolution by 2. Okay, resolution by 2. And resolution, how we can find out? Resolution is equal to VFS, that means full scale voltage, divided by 2 to the power n minus 1. Okay, so here full scale voltage is given, that is 10.23, and already given n is 10, that means 2 to the power 10 minus 1, right? So here 10.23 divided by 1024, if you will multiply minus 1, we will get 10.23 divided by 1023. If you divide it, you will get 10 millivolt. Okay. Now quantization error. Quantization error is equal to resolution divided by 2, that means 10 millivolt divided by 2, that is 5 millivolt. So answer is 5. Okay, so if this type of question is given, they have asked for quantization. So for quantization, it is a formula resolution divided by 2, and here the formula of resolution. Okay, okay, so moving to the next question. So next question is, for a 10-bit digital ramp ADC using 500 kilohertz clock, the maximum conversion time is. What is the formula for digital ramp ADC conversion time? Digital ramp ADC conversion time is, formula is, that is 2 to the power n minus 1 into t clock. Okay, where n is the number of bits and t clock we need to find out, because here it is given the frequency. So f is given 500 kilohertz. Now we need to find out the t clock, that is 1 by f, already we know that. So 1 by 500 into 10 to the power 3, so that is 1 by 5 into 10 to the power minus 5. If we divide, so you will get 2 into 10 to the power minus 6. We can write 2 microsecond. Okay, we can write it as 2 microsecond, right? So now put the conversion time formula. So 2 to the power 10 minus 1 into 2 microsecond. Already it is given the answer microsecond. So 1024 minus 1 into 2 microseconds. So we will get 1023 into 2 microseconds. We will get 2046 microsecond, right? 2046. So just check in the answers. So option 3 is the correct answer for this question, 2046 microsecond. Okay, so moving to the next question. So next question is a 5-bit ladder has a digital input of 11010. Assuming that 0 corresponds to 0 volt and 1 corresponds to plus 10 volt. Okay. So the output, its output voltage will be, what will be the output voltage? So already we know that the output voltage for a ladder type, output voltage for a ladder type, that is type ADC, digital to analog converter, is, that is resolution multiplied by decimal equivalent of binary, right? Equivalent of binary input. So what will be the decimal equivalent of this binary input? That is 11010. What will be the decimal equivalent of this binary? Any one of you want to let me know what will be the decimal equivalent of this binary? And resolution, already we know that the formula of resolution, that is V reference voltage divided by 2 to the power n. Here it is not given to full scale voltage, that's why we will take the 2 to the power n only. If it is given the full scale voltage, in the formula you will get 2 to the power n minus 1. Okay. So reference voltage already corresponds to 1 is given, that is 10 volt. Okay, so 10 to the power, it is a 5 bit, n is equal to 5. So 10 by how much? 32. So if you divide it, what we will get? Yeah, someone has answered. What will be the, and also check for 10 by 32, what will be the value? Yeah, that is 26 in decimal, right? Correct one. Decimal equivalent is, that is 26. And what will be the value of 10 by 32? That is 0. If you calculate it, you will get 0.3125. Okay, now just multiply these two. Resolution, we have got 0.3125 into 26. We will get 8.125 volt. Okay. So here only positive has been taken, no negative have been taken. So we will consider only positive one, that is 8.125. So that's why option 4 is the correct answer for this question. Okay. So moving to the next question. So the resolution of an 8-bit DAC, digital to analog converter, will be, what will be the resolution? What will be the formula of resolution? Already if you have gone through the slides, it is given formula of every values, that is resolution and error, how to calculate error and all those things. So 1 by 2 to the power n minus 1. Okay, so n is given only 8 bit, so 2 to the power 8 minus 1, that is 256 minus 1, that is 1 by 255. Okay, this is a formula of resolution to the power n minus 1. So option 1 is the correct answer for this question. Okay, so here input voltage is not given, otherwise it is V by 2 to the power n minus 1. So we have taken as a 1. Okay. So moving to the next one, a 6-bit ladder digital to analog converter has a maximum output voltage of 10 volt. The output for input 10110 is approximately what will be the output for the input. So again, with the same formula, we can calculate it. So V out already we know that is equal to resolution into decimal equivalent of equivalent of binary input. So binary input is 101001. So what will be the binary equivalent of that 1? What will be the binary decimal equivalent of this binary? If you calculate it, okay, so binary equivalent of this one we will get. So my it's not working. So just start. What will be the binary equivalent of this one? That is 41. Okay, so now we need to calculate the resolution. So in the same way, so I am representing resolution by R. So V reference by 2 to the power n minus 1. So we reference maximum output voltage is given 10 volt. So 10 volt divided by it is just 60. So 2 to the power 6 minus 1. Okay. So if you calculate it, so you will get 10 divided by 63. If you divide and multiply it, divide it, you will get 0.15, or you can say approximately 0.16 you will get. Okay, now multiplied with resolution with the decimal equivalent in order to find out. So V0 is equal to 0.16 multiplied by 41. Approximately you will get 6.5. Okay, so that's why option 2 is the correct answer for this question. Okay, already you know that this one all one are formula based, so you can solve it. So now next one is if the resolution of a digital to analog converter is approximately 0.4%, it is given in a percentage of its full scale range, then it is in, now we need to find out the n number of bits. So already we know that formula of resolution, that is R is equal to 1 upon 2 to the power n minus 1, right? But if we want to find out in the percentage form, percentage of resolution, so what will be the formula? So 1 by 2 to the power n minus 1 into 100, right? If we want to convert it into percentage, so already it is given, resolution percentage is given, that is 0.4. Now what will we need to find out? Percentage, to the, so we can write it here like this: 100 divided by 2 to the power n minus 1. What will we will get? Yes, someone can you please share all formulas listed together? Okay, I will try. So can you find out what will be the value of n? Directly here we need to multiply and just divide it. So if we take 2 to the power n minus 1 this side, and if we put the 100 divided by 0.4, so what we will get? Here I am writing 2 to the power n minus 1, 100 by 0.4, divide 0.4 equal to, we will get 250. Okay, so 2 to the power n is equal to 251, so which is equal to 256 equivalent. So 2 to the power 8 is equivalent to, we can't take 2 to the power 7 because it is very much less than the 251, so approximately we can take. Okay, so n is equal to 8. Okay, so from here we can get it like this. Okay, so have you understand this question? Actually my pen is not working, so that's why I'm not I'm not able to write it correctly. So but I think, I hope all of you got this question. So here just we have to
Yes,
take,
ma'am.
yeah, so n approximately we will get 8, so it will can be a 8-bit converter. So option 3 is the correct answer for this question. Okay, so okay, thank you. So for this week, these are the questions. So if you have any doubt, you can ask. Otherwise, we can close this session for today. Okay, so thank you everyone. Thank you for joining this session. Now, if you don't have any doubt, you can leave the session. Okay. So anyone of you have any doubt, so you can ask. Otherwise, we can close the session. Okay, okay everyone. Okay. Thank you for joining. So I hope all of you have don't have any doubt.